Institute of Fundamental Research, Mumbai.
Okay. Thank you. Good afternoon. I'm Dibyasankar. I'm from Tata Institute of Fundamental Research, Mumbai. And in the backdrop, you see a beautiful institute beside Arabian Sea. So today, I will describe my recent result on magneto-modulated reflectance study I have done on bulk 2H MOS2 and how I have used that to extract exciton G factor using that technique. So, as introduction, I can say that we all know these excitons in these TMDs are strongly bound, and even till room temperature, they govern the optical properties basically. So it's important to study their properties. These TMDs have novel spin-related properties, and some of them are revealed under magnetic field studies. One of those properties is exciton Landé factor, which helps us to understand the details of electronic band structure and what is the orbital contribution in the electronic band structure. But we see that for in these TMDs, if we want to extract this exciton Landé factor, it actually requires very high magnetic field, and also the flakes are very small, so we need very high spatial resolution also. So the question we asked that, can we measure the same exciton Landé factor using low magnetic field and a setup which can be easily compatible with microscopic arrangements. So our system is bulk 2H MOS2. This is the crystal structure, and though it's not a direct bandgap material in bulk form, but the smallest direct gap forms around the K point of the Brillouin zone. And that point is interesting because in monolayer, the direct band forms around that point. So we need to study, it's important to study the band structure around that point. So we explored this magneto-modulated reflectance MMR spectroscopy to measure the exciton Landé factor. And we have utilized the fact that it is a very sensitive measurement, and very small spectral chains can be picked up by this magneto-modulated measurement. So what I have studied is, like, I have extracted this Landé factor for A1s exciton and interlayer exciton around the smallest direct gap into HMS2. Just want to give emphasize, like, we're here in talk, in several talks we have seen interlayer exciton in hetero structures, hetero layers, but this is homo layer actually, it's a bulk system. And how I understand this exciton as I've shown schematically here, if you put the hole in one layer and you try to find out what is the wave function of this interlayer exciton, you will find that the electron lies in the other layer of the adjacent layer to the hole. So in that sense, it is interlayer exciton. Okay, so the working principle we started with, like, we know that in case of gallium arsenide quantum wells, if we don't apply any magnetic field, the conduction band and the valence band, their spin degenerate. And if you want to probe the system with one circularly polarized light, it cannot distinguish between two states. But as soon as you apply magnetic field, there will be Zeeman splitting, and now you can selectively address one state with, say, right circularly or left circularly polarized light. Similarly, for negative magnetic field, you can address the other state with the same polarization of light. So mathematically, I can just show that this exciton transition energy will be different for positive V and negative V, and this expression is this. And so if we somehow can measure this delta E, the difference between transition energy of these excitons, from this expression we can get the exciton Landé factor. One thing to mention is for sigma minus polarization, this delta E sign will be opposite. I will show you that how that is reflected in my measurement. So schematically, I just want to say how it is happening. So this is a standard reflectance spectrum of for exciton. And so if we apply magnetic field, there will be a shift in the transition energy, but the order of shift is the delta E is order of micro electron volt, which virtually cannot measure by subtracting two signals by doing a DC measurement. But there comes the importance of AC measurement, this delta R by R kind of measurement. There, the same thing will give rise to a peak above zero background for positive G factor, and similarly for negative G factor, it will be a dip. So for small changes of delta E, this delta R by R spectrum, the peak of that is actually proportional to delta E. And this overall MMR signal, it depends on the exciton parameters, how sharp it will be, and height, all these things. And and other thing is how much your modulating magnetic field is. So how we extract these G factors, that we initially simulate this R spectrum using Lorentz oscillator model of exciton contribution to dielectric function, and then we artificially put delta E to Zeeman splitting to this R spectrum and try to simulate this MMR spectrum. From that you get delta E and you plot it with magnetic field. From the slope you get the G factor. So the experimental setup is very simple. We start with a polarized light, it passes through a polarizer, then a quarter wave plate, so circulative polarized light, then through a 10x objective on the sample it at cryogenic temperature, the liquid helium, and the solenoid, it is placed around the sample, which is actually modulating the magnetic field. Then the reflected light goes back through the same path and reflected from the beam splitter, directly falls on the photomultiplier tube. And we have made a camera arrangement to see the spot on our sample. So this is actual setup image. You see the solenoid there and the rest of the optical arrangements. Two things to mention. One is the spot size of my setup is order of 50 cross 100 micrometer, and the RMS magnetic field I'm getting from my coil is order of 50 millitesla at 175 hertz. So with that, we tested our setup with a very known, well-studied sample. It is gallium arsenide, aluminum gallium arsenide quantum well. So we had a 4 nanometer quantum well. So what you see here, this red curve is the measured reflectance spectrum, and the black one is the simulated spectrum using the model I have shown you before. So here you see two distinct transitions, one for light hole and another for heavy hole. So this is the corresponding MMR spectrum. There you see there are distinct transitions, but the magnitude are very different. In R spectrum, this light hole has a very small magnitude, but in MMR, that actually dominates. So it suggests the G factor corresponding to light hole is higher than G factor of heavy hole. And also the spectral feature, if you follow just one curve, so if we follow only the red curve, you will see this goes like dip and peak, but it goes like peak and dip. So it shows like the G factor, the sign of the G factor is different for light hole and heavy hole. So we have extracted that. For heavy hole, the G factor is minus 0.6, and for light hole, it is plus 7.5. And this is the thing I promised you before, that you see for two orthogonal polarization, the spectrum actually flipped by 180 degree. And this measured G factor values, it moderately matches with the already reported values. So the limitations, like in our system, what we have felt through the experiment, that the magnetic response of different optical elements can contribute to a large background, which we need to subtract all the time. And in the course of experiment, we discovered that this beam splitter material they use is something called inconel, which is affected by magnetic field. So we have built a aluminum coated beam splitter in our lab and used that as in our measurement. And the error in G factor measurement is mostly dominated by signal to noise ratio. But other thing is like several exciton parameters determine that how low G factor you can measure. So for this gallium arsenide case, this is the simulation for that. For 50 millitesla magnetic field, so it's a 2D plot. One x-axis is oscillation of the exciton, and the y-axis is broadening of the exciton, and you see several contours. What is the minimum measurable G factor in this condition? So we can say in our system, in the case of quantum well, we cannot reliably measure G factor below 0.5, but above 0.5 we can measure. So with that, we applied this same spectroscopic measurement on exfoliated bulk 2H-MOS2. And here you see again the rate curve is experimentally measured arc spectrum. So you see two dominant features here, A and B. Those are corresponding to spin orbit interaction splitting, and but there is a very weak feature just adjacent to A, which the origin of that feature is kind of debated. People have previously assigned that as n equal to 2 excited state of A exciton. So we did our MMR measurement around this point only, and if you see the curve again, if you follow the rate curve, you will see here this feature is very minute compared to this 8 exciton feature. But here you see the peak intensity is almost comparable, and also this is a peak, but this is a tip. So just by looking at the curve, you can say that the G factor corresponding to A exciton is very much small on that of this X transition, and also the sign should be opposite. So so our measured G factor is for A exciton it is minus 2.5, and for this X exciton it is plus 11. So drastically different G factor, so the origin cannot be n equal to 2. So what it's likely to be is interlayer exciton. And a little bit how I understand this origin of interlayer exciton is represented here. So there is some property in this material which is called spin layer locking. So we know that two adjacent, so same valley in two adjacent layers have opposite spin. And if you see this interlayer transition, the carrier spin forming interlayer transition and intralayer transition are different. So this is down, down, but this is up, up. So it kind of explains why the G factor should be, the sign of the G factor should be opposite, but why the value is very large, positive 11, that we still don't know. So in summary, I can say that I have shown you my result on Magneto-modulated reflectance spectroscopy with very low magnetic field Auger of 50 millitesla, and my measurement with high spatial resolution and cryogenic temperature. And I verified the existence of interlayer exciton in bulk 2H-MOS2 with a large positive G factor, though the corresponding explanation why it is the value is so large, we still don't have that. But I think DFT-based calculation may help us to understand that. So with that, I want to acknowledge whatever support I have got from TIFR and the financial support from Infosys Foundation. Thank you for your attention. I will leave you with this scarf. So if you have any question, you may ask.
All right, if we have any questions for the speaker, please come to the microphones in the aisle.
I don't know if you're familiar, but for bilayer systems, G factor of excitons, interlayer excitons was measured, and it was minus 15, right? So is it similar to yours?
15?
15, minus 15 here for interlayer excitons.
So the result I know about it shows positive 8. So there is a paper, huh?
Depends on orientation of in bilayer. For parallel alignment, you have one G factor.
Right, yeah.
But you study
So,
Okay.
just if you're familiar with these papers, you could use them. Or if you don't, if you're not, I can give you the references.
I will talk with you. I'm not aware of. Yeah.
Okay then.
Any other questions for the speaker? All right, then let's thank this our speaker again, and we'll move to the next talk. The next talk is given by Yishun Chen from Monash University, who will tell us about P-type ohmic contact monolayer tungsten diselenide field effect transistors using high electron affinity amorphous molybdenum trioxide.